Welcome to this video on the road to quantum reality. In this video we are going to extend the work on motion and phase harmony in one dimension to cover motion in 2 or 3 dimensions. Just a word of warning. In this video there is quite a bit of algebra going on. If it is the sort of thing you enjoy or you want to check my workings, and by the way, please do, because I'm working on my own, it's essential that someone checks them sooner or later, then please enjoy. But if not, you can fast forward judiciously to the end of each algebra section and pick up on the findings. These are way more important than the details. I like to think of the maths as a black box. The important things are what went in and what came out. First, a quick recap of what we found in the previous video. What we put in, so to speak, was the requirement for phase harmony in a row of FRs moving through the ether. We showed that this meant that FRs must exist at the nodes of a travelling standing wave, which sounds a bit crazy, but by which we really mean a standing wave moving relatively slowly. We were able to investigate such a wave by considering it to be formed from waves emitted forwards and backwards from the moving row of FRs and applying the appropriate Doppler shifts caused by the motion. Then we showed that it was possible to factorize the summed waves into the product of 2 other waves, which we called the phase, or P wave, and the standing, or S wave. Evaluating the characteristics of these wave factors, we showed that the wave vector Kp of the phase wave was proportional to the velocity at non-relativistic velocities, and that the standing wave had a shortened spacing between FR locations. We also showed that the product of the 2 phase velocities was c squared, which is what de Broglie found from relativistic considerations and his own version of phase harmony. But what we found was not consistent with special relativity because we had a factor of gamma squared rather than gamma in our equations. What was really revealing from the 1D analysis is that it showed a link from real wave quantum mechanics to the wave with wave vector proportional to velocity, which in quantum mechanics was fed forward to provide an input to the plausibility derivation of Schrodinger's equation. We also noted that the S wave is essentially absent from quantum mechanics. To do the necessary calculations for 2 or 3 dimensions, let's look at a completely general setup, by which I mean FRs not arranged in any particular locations, such as a grid. Put 2 FRs at S for source and T for target at a single instant of time. Again, considering a general case, the 2 FRs can have different phases, and the phases at t equals 0 are indicated by the direction of the arrows. The difference between the 2 phases at t equals 0 is phi st. Actually, I notice I've written phi 0 in this diagram, but life's too short. The direction of motion at velocity v is to the right in this picture, and the separation between the 2 FRs is L right arrow in the direction of motion and L up arrow orthogonal to this direction. The frequency of the FRs is omega. Now, after a short time delta t, the FR at t moves to location t prime. The one at S also moves, but we are only interested in the phase it had at t0, as this dictates the phase of the wave arriving at t prime. Now, in the spirit of a black box calculation, I will spare us the full algebraic manipulation, but I will say how it was done. Essentially, we apply Pythagoras' theorem to the right-angled triangle with sides L right arrow plus V delta t, L up arrow, and finally hypotenuse C delta t. Delta t is present in two of these sides, so we get a quadratic for delta t, which we can solve to get the resulting equation. Note that this is the 3D version, although the diagram is only 2D. And now we can apply it to our presumed grid of FRs, and we assume motion along the X grid axis, so the source is A and the target is C. We will just check our findings from the previous video by setting L up arrow to 0. By the way, remember, in applying this equation, L up arrow is the distance between the source and target orthogonal to the direction of motion, not the actual distance. And the distance in the direction of motion we found to be contracted using the gamma squared factor. We need the initial phase difference between the source and target, and we can readily find this because we had an expression for Kp shown in the green box, which is essentially the change of phase per unit distance, and we also know the distance, so we just multiply them together to get the initial phase difference. When we make the appropriate substitutions, we arrive at the orange expression for the initial phase difference between source and target FR. We can put this into the general equation. Also, we put in the expression for the separation in the direction of motion as a function of velocity, and note that the physical separation in the y and z directions are both 0. When we open the square brackets, the first two terms are seen to cancel, and the square root contains a perfect square, so we can remove it. We are not too worried about which root to take, because all we want to know is that the difference is not a function of v or gamma, which is of course also a function of v. And we see that this is indeed the case, because the gamma term now cancels. So the phase difference does not depend on v, which is exactly the condition for phase harmony. Be very clear that the phase harmony condition does not say that the phases must be the same, only that the difference between the phases, whatever it is not changed by motion. What we have done thus far is to confirm that our original 1D results involving a gamma squared factor can also be demonstrated with this general equation. But now we look at the phase of FRs in the orthogonal direction, when the source is A and the target is B. In this case, the separation in the direction of motion L right arrow is 0, and the separation orthogonal to this direction L up arrow is 1. The initial phase difference, phi st, is 0 because the phase gradient is in the rightward direction. The general expression then reduces to the one shown here, and we can factorise the bit in the square root as shown. Now recall what gamma actually means by looking at this equation in brown. We can square it to get rid of the square root, then sort out the fraction, and finally isolate c squared minus v squared as shown. And this can be substituted into the green equation. Once again, we have a perfect square within the square root, So we can end up with the required expression for psi AB prime. But this contains a gamma, so it varies with V. In other words, our original findings for one dimension do not extend into 2 or 3 dimensions. There are a lot of things we could try to sort this out, but we already know that the answer in nature is special relativity, so we might as well try this straight away. The expressions we will need encapsulate the time dilation and length contraction of special relativity and are these. And we can calculate phi st using their product as before. Kp includes an omega, which we previously took to be unchanging, but which we must now recognise as changing with V as shown. Making the appropriate substitutions, we get the Brown expression for phi st, which we can put into the general equation. When we remove the square brackets, we note that the first 2 terms cancel, leaving the equation at the bottom of this slide. We can reorganise the bit inside the square root by first separating the term in Lx from that in Ly and Lz, and then refactorising the latter in terms of c squared minus v squared, remembering that we have already found this in the Brown equation, which gives us this. But now c squared upon gamma squared is a factor, and because it is a perfect square we can remove it, and we see that gamma cancels, leaving an expression which does not depend on v. Remember, we have done this for the general case, so it will apply to any structure we might consider. The relative phase between any 2 FRs is unchanged by motion through the ether because phase harmony leads to the special relativity time dilation and length contraction. We can recalculate some of the wave characteristics for the combined real wave sum and its S and P factors. We start off with these red ones, which are essentially the special relativity relationships which we assumed and have just tested. Then we have these blue characteristics of the P wave which follow from the red ones. The lower one is the one which gives us the relationship between K and V, which is fundamental to quantum mechanics. The upper one we haven't yet interpreted, but we will do this in the next slide. The S characteristics don't really have a direct interpretation and do not arise in quantum mechanics. And finally, these characteristics can be shown to exactly replicate de Broglie's velocity relationship. Now let's look at the interpretation of omega p. First, we can substitute this now varying omega into the relativistic k expression to give this. What happens if we make the same assumption about omega p as de Broglie did when he equated h bar omega p to mc squared? If you missed this, it is discussed in full in the video on de Broglie earlier in this series. In essence, he says that the frequency of the P wave is an indicator of the relativistic mass of the particle. Well, in a couple of easy steps, we end up with exactly the de Broglie relationship P equals h bar k. This has been a lot of algebra, so let's summarise it a bit. Firstly, if we assume that phase harmony is a requirement for motion through the ether in real wave quantum mechanics, then it is satisfied by special relativity like time dilation and length contraction. Interpreting omega p as the relativistic mass brings real wave quantum mechanics exactly into line with quantum mechanics. We haven't scaled the real wave quantum mechanics theory up to now, but this means we can do it. Remember, when the velocity is zero, the clock aspect of the particle and the frequency of the p wave are the same, say omega naught. But if we set this frequency, we also set the wavelength, in this case to the Compton wavelength. But that means that real wave quantum mechanics is saying something important which quantum mechanics does not, at least directly, say. It says that you cannot have structures which are too close in size to the Compton wavelength because you lose the ability to interact between FRs. And of course, single particle quantum mechanics does fail at around this limit. The argument is that it requires so much energy to constrict a particle to this size that instead we get two particles. Have we shown that real wave quantum mechanics underlies the relativity principle? Well, not entirely. At reasonably non-relativistic speeds, it would explain relativistic results, such as global positioning satellite clocks slowing, because SR is the asymptotic result for real wave quantum mechanics structure motion at low velocities. But at highly relativistic velocities, we must be concerned about amplitude effects, because spiral waves have to travel further in the forward direction than in the backward direction. We seem to be showing that special relativistic behaviour is to be expected, but it might be a step too far to have a relativity principle, as in the laws of nature are the same for all inertial observers. But I don't know about this. It needs more work than I am able to give it. Anyway, well done if you've got this far. It's a lot of algebra, but a couple of animations will make it a bit clearer, I hope. In this first one, we look at structures moving at various velocities to the right. Although it looks one-dimensional, we are of course applying the special relativity compatible equations which we found by consideration of phase harmony in 2 or 3 dimensions. You can think of us looking side-on at a structure which extends into the screen with multiple parallel rows. Each of the rows in the graph relates to a separate velocity, and they are being shown on the same animation for comparison purposes. The small black arrows represent the phase and location of an FR. The location is the root of the arrow, and the direction of the arrow indicates phase. The x-coordinate of the tip of the arrow has no spatial significance. The y-coordinate of the tip could be seen as indicative of the amplitude of a linear oscillator placed at the root of the arrow. If you recall, de Broglie supposed such a thing in his original phase harmony work. But we are interested in the phase of a rotating object, not a linear oscillation, so we need the rotating arrow. The red line moving right and the blue line moving left represent the crest of a wave moving at the velocity of light, which is 1 for us. Because of this, you can see that as these lines pass through an FR, the FR phase arrow is always pointing in the direction of the crest. The top animation is for a stationary structure. The P wave has k equals 0, so there is no waviness in space. If you watch the video on de Broglie, you have noticed that it is the same graph, except that where he considered a single point oscillator, we have an extended row of rotators. Any one of our FRs could be viewed as a de Broglie particle if we only thought of it as an oscillator rather than as a rotator. And so it is that when we start the structure moving to the right, we see the emergence of the P wave, which is exactly the same as de Broglie's matter wave. The difference is that now we have an obvious interpretation for it. It is giving us the relative phases of the FRs required for our extended version of phase harmony. The other rows show increasing structure velocities and higher K values for the P wave. If you look at the bottom one, for V equals 0.8, you can see the source of our concern for these higher velocities. The blue wave, going left, passes through the FRs very quickly, thus travelling a short distance, whereas the red line, moving right, is chasing the FR in front and has travelled a much longer distance. This would result in amplitude effects that require a much more careful analysis. Moving on to the next animation, we are now looking down, as it were, onto a physical grid, and we are only considering a relativistic velocity of 0.4. The purpose of this animation is to illustrate how phase harmony is working in 2 dimensions. Now, apart from the red and blue lines representing forward and backward wave crests, we introduce the yellow and green lines representing a wave crest from one FR to its orthogonal neighbours, which of course are no longer orthogonal when the waves arrive. These waves have a significant component in the direction of the structure's movement, hence they are diagonal. You can see that as they cross each FR, they coincide with the FR phase, which is the hallmark of our extended phase harmony. It is as well to remember that we have done all of the above work on the basis of FRs moving bodily through the ether. We found that the momentum is proportional to the wave vector of the P wave, exactly as de Broglie did, and as assumed in quantum mechanics. The wave vector is the same thing as the gradient of the phase. It is phase per unit distance. This might give us pause for thought when we move on to consider orbital angular momentum in the next but one video. But first, we are long overdue in validating our claim that real wave quantum mechanics predicts spin as h bar over 2. We have had to wait until we found the correct scaling for real wave quantum mechanics in this video, i.e. the Compton frequency and Compton wavelength, before we could take the final step. But we will do this in the next video. Thank you for watching this video. Please stick with it, as there are a few, to my mind, amazing insights to come. Please like and subscribe, and don't forget to tell all your physicist friends.